video is going to be a review of an experiment that I'm involved in with wavelength division multiplexing. It's a fancy term that's used to describe effectively the overlaying or the interspersing of multiple colors of laser beams into a single composite laser beam that has the properties of the individual subcomponents. In a normal display projector, which is called an RGB projector, you may have three primary color beams, blue, green, and red. And because the wavelengths of these lasers are so far apart in the spectrum, you can use bandpass filters or dichroic filters to allow you to take two intersecting beams of light, and at their intersection point, allow the beams to pass through a filter. The filter allows the one beam to pass through unaffected and reflects the other beam into the primary beam to produce a collinear and parallel beam that is made up of the two composite beams that were combined in the filter. That's possible to do when the wavelengths are far apart. But when the wavelengths become very close, let's say for example I want to take multiple red lasers, all very similar in wavelength but not identical, and I want to combine them, you can't use the filter technique simply because they have a slope or a acceptance such that they can't exclude or include very closely spaced wavelengths. They'll treat both wavelengths the same. They'll either reflect both or they'll transmit both, but you can't use a filter to be able to combine very closely spaced beams. I suppose in theory, if you were to develop a huge stack of interference layers and you produced a very customized filter, you might be able to take two specific red lasers and put them on top of each other. But if you wanted to put 5, 6, 7, 8, or 9 lasers, all slightly varying in wavelength, on top of each other, it'd be prohibitively expensive. The way that you can do this, though, and it's been done by communications companies and also by high-end diode manufacturers in order to be able to pack additional light into their fibers for data communications, increasing bandwidth, or increasing the power in a fiber. Using a dispersing element, you can fan or bend beams to a common point, say the entry point on the fiber. And by manipulating the entry point, you can cause those beams that have moved inward on each other to become parallel again once they've entered the fiber. That technique, though, requires very special lasers and is expensive to design and engineer. And in my experience, it's only available for the infrared. What I'm going to demonstrate is sort of a do-it-yourself version using commonly available powerful red diodes that allow me to build up the brightness of a particular laser beam by taking advantage of the fact that these aluminum, indium, gallium lasers are very sensitive to temperature in terms of their wavelength. So if you cool one of these lasers, you can vary its wavelength from its stock frequency to some blue shifting or some shortening of the wavelength, and the more you cool it, the more you shorten it. So by adjusting the temperature of individual diodes, I can effectively adjust the wavelength of the individual diodes and take advantage of the same process. To lay out the way that the process works, I'll show you the apparatus that I built to do this. If you look inside of this box right here, you'll see three brass housings that each contain Mitsubishi P73 multi-mode diodes. Each one of them produces about half to 1 watt of red light centered around 536 nanometers. The housings have a ESD protection device on them. They contain 2mm aspheric collimator lenses in front of each of the diodes, and the setup is run in series from a single common power supply back there. So as a result, each of the diodes gets the same current. They're just sharing a voltage drop from the driving voltage that's supplying the apparatus. The three brass mounts, if you can see down below, are mounted on a stainless steel bar. The bar is clamped at one edge to a spacer. That spacer is equally thick as the two-stage Peltier or TEC cooling device that's mounted on the other end. By clamping the bolt down and squeezing this bar down, it squeezes the TEC and effectively forms a thermal loop, so that the TEC, which cools its upper end and hence the stainless steel bar, dumps its heat into the main base plate here, which is carried away by the cooling loops here from this water heat exchanger. The room temperature base then allows the heat that would be present in the base and is in contact with this end of the bar to move up into the bar and therefore across to the cold side, forming a gradient of temperature. Stainless steel has a very poor thermal conductivity, and the addition of the holes that I've placed between these diodes increases the gradient even further. So for a given amount of heat load passed from one end to the other, there's a gradient in temperature. The diodes ride this temperature gradient, and so as a consequence, this diode here is the warmest. This is next cooler, and this is the coldest. By taking advantage of the relatively powerful TEC, even though this system works rather poorly for controlling the temperatures of these diodes, nevertheless it produces enough of a gradient that I'll demonstrate the wavelength shift between these things allows me to do the multiplexing. Out of the end edge, or the outside of this hermetic package, which effectively just prevents air transfer from the room to the inside of the chamber, so that the cold end, which condenses some of the water vapor trapped in there, doesn't continue to pump water vapor out of the air. Once it's dehydrated the inside of this chamber, no more condensation occurs. That's the reason for this box. These three windows, which are anti-reflection coated, are mounted at a slight cant so that the light that passes through them, some of it will reflect back simply because the anti-reflection coating is not perfect. That will then strike the sides of the diode supports somewhat off-center and therefore not directly back into the diode, potentially damaging it. The three beams that come out of the end of these windows then strike these three knife edge holders that hold three prisms that are coated to reflect the red light that comes out of the diodes. If you look carefully, you'll see that these flex mounts, or these mounts that support the prisms, are not mounted in line. They step backward. As a consequence, the first beam that passes out of here, as anybody who's familiar with knife edging would see, is that this beam is reflected at right angles in front of the other lasers. This beam then therefore travels slightly past that point through the initial beam and is then lined up next to it, and finally the third one lined up next to it. If I place this relatively low reflectivity anodized aluminum here, you can see the three beams that are coming out are almost touching each other. The reason for the knife edging is basically to remove the inevitable spacing that's required by the mechanics and the electronics of the diode to produce as dense a beam as you can, given the fact that the beams have to be adjacent to each other in this setup so far. If I were building a projector with multiple diodes, I would end at this point. I would have a beam that looks somewhat rectangular, made up by three individual stripes, and that would be the beam that would be sent downfield to project onto a screener and to form beams into the air. You cannot make this beam any brighter. You could make it more powerful by making it bigger by adding additional diodes, but they're always added adjacent to each other. There's no way to put them within each other unless you use this multiplexing technique. The beam then travels to this prism, and when it hits the prism, it's deflected by the prism, it's refracted, and sent over to this mirror. The refraction is exactly the same angle for these three diodes, which are currently all at room temperature. If you look behind this structure here, you'll see these thermistors that have been set up to measure the temperatures of the cold plate at each end and each one of the diodes. There's effectively 5 different channels here. Right now, we're accessing this channel here, which represents the coldest temperature at the top of the stainless steel, and 2 other channels here which represent the other 2 diodes. So we have, 2 diodes that are mounted, These 2 readings read the 2 diode temperatures from the cold end, the next cold end, and effectively the warmest end. And you'll see as this stabilizes, these temperatures will vary linearly with the position of the diode on the bar. In any case, because they are at room temperature now, the 3 beams that enter this prism here remain 3 beams outside of the prism. They're continually growing longer simply because of the divergence of this very multi-mode diode and the very short focal length of the converging lens. But you can see they are still 3 individual beams. They pass here and they hit the other prism, which I'll explain in just a second. Some of the light is reflected off the edge of the prism. As you can see, it's traveling in this direction here. Eventually, that light will strike this mirror over here. This is the reflected light that is only passed through one prism. That light is then reflected all the way across the room to the shorter or closer of the 2 mirrors. The reason this mirror is in front of its partner is because that beam of light has had to travel further in that direction, so that the net result is when this beam is then retro-reflected to the screen, which is this beam here, as you can see. This beam has traveled the same distance as the beam that has gone through the prism. The reason that the beam that's gone through the prism is brighter is simply about 85% of the light actually transmits through the prism is deflected once again to what you can see is 3 simple stripes. And if I get a little white piece of paper here, I'll demonstrate that the 3 stripes are still present. They're close to each other, but they're still obviously 3 individual stripes. This then travels all the way across the room to the farther of the 2 mirrors, and then back again here. The fact that this is slightly narrower than this has to do with the anamorphic property of these prisms. It's a secondary issue that can be compensated or factored out. You could use lenses to correct it, but effectively passing through these relatively massive or thick pieces of glass essentially broadens out the laser stripes in the near field and decreases the divergence in the far field. That's a side effect. It's nothing to do with what we're going to be demonstrating now, but it's one of the reasons why the beam here appears to be a little bit sharper. In addition, of course, very much brighter. What I'm going to demonstrate now, though, is what happens when we cool the beams. When we cool them and these diodes change their wavelength, the light that comes out of here no longer will be coming out of here parallel. One of the beams, the bluest beam, will be refracted slightly more strongly and be drawn into the other beams. And as we do that, you'll see, it's too bright. You'll see that these 3 beams at this position here will begin to draw together. I'm going to go ahead over here and I'm going to turn on the cooler, which is going to pump about 120 watts into the base of the stainless steel block. The temperature takes a long time to stabilize, and I'm not going to keep you here for 10 minutes just staring at the thermometer. But what I will do is I will show what happens as the laser begins to cool off. This beam here, which represents the reflected beams, which were parallel upon hitting the surface of this prism, but which, because this prism is no longer going to be seeing exactly the same wavelength, will begin to produce a refractive differential between the beams, and the beams will begin to draw apart. You'll only see that in the reflected image because the beam that goes through the second prism is then inverted. The convergence angle is reduced, essentially eliminated, at the point that the beams have all reached the same narrow stripe. So they've all been brought down to the same point, and then this prism here leaves them at the same point. You can see already, just from the small amount of cooling, that this is beginning to open up. That stripe is no longer perfectly sharp, but you can see that the stripe over here hasn't changed, and it shouldn't, because it's been compensated by the prism. As time goes on, you'll also notice that the 3 stripes that you used to see here will begin to narrow further and further. As they narrow further and further, that means the convergence is increasing, the angle is increasing, and you'll notice the effect is that the stripes on the other side, the part that are not compensated, begin to open up. So I think what we'll do right now is we'll take a little bit of a break, take a look at the temperatures just so you can see that things are in fact changing. This is the temperature on the cold end of the stainless steel. It has a slower response, and so it's lagging behind. This is the temperature of the coldest of the diodes, of the first laser. This is the bluest of the lasers. And if I show you this other image here, this other reading, the warmest diode and the next warmest diode have barely changed temperatures. There's a great lag, and that's why you can see when you look at the stripes up above, only two appear to be separating. The very coldest diode, while the two diodes here that are taking a long time to equilibrate are still running almost the same temperature and therefore almost the same wavelength. So before we take this little bit of a break, if you look back up at the screen, you can see what's happening to the reflected beams. So I'll see you in just a couple minutes. Welcome back. It's been about 6 minutes and I've allowed the temperature to approach stabilization, and if you look over at the thermometers, you'll see the temperatures of the different components. This is about 2 degrees from stabilization, but at minus 22 degrees represents the temperature of the coldest part of the stainless steel bar. This is not where the diode is. This is right on top of the Peltier cooler. If you look over here, this temperature here, the minus 10, represents the temperature of the coldest diode. The next temperature here, 11.3, represents the temperature of the next coldest diode. So there's almost a 20-degree differential there. And then finally, the temperature here, 16.5, represents the temperature of the warmest diode, and finally 17 degrees here represents the warm end of the bar. So as you can tell, there's a very large differential between one diode and the next, and a relatively small differential between the second diode and the first diode. If you look up at the screen now, you'll see that this has also been represented in the differential spread of the diodes from the first prism. This wavelength here, which represents the coldest diode, if I put my finger in front of it right here or block it, you'll see that what happens is this is the coldest, this is the cold end of the box. If I block this, this is the one that is farthest from its compatriots. The second diode over here, which is the middle one, is close in temperature to the third one here, which is represented by the third diode. You'll also notice too, if you look, even though these have obviously spread out unequally, but nevertheless spread out, this over here has remained quite sharp. So obviously we've had an effect on the light as it's passed through the first prism, and we've negated that effect in the second prism once the beams were aligned. To prove that the beams have now become narrower, if you come around with the camera, I was told that this is so bright that you may not in fact be able to see that it's moved from 3 individual stripes to now a single thin stripe that has the width of 1/3 of the original 3 stripes. It may be too washed out to see this at that point, but if you take a good picture of that with the polarizing filter, and then I go ahead and let everything warm up, you can take a look and you'll see the 3 stripes again reappear. Okay, so that's now what the 3 beams have become after they've converged through this first prism, bounced about 300 millimeters over here to where the second prism is located. You'll see a single stripe. Now, because we're using the polarizing filter and you don't wash this out, you can see how fine that stripe is over there. It's below my measurement there. It's probably a millimeter wide or so. If I turn the coolers off now, you'll see this corresponds to the current setup with the lasers. 3 spread out, 1 still perfectly co-aligned. If you take a look at this single stripe, I'm going to turn the cooler off. We'll take another little bit of a break. Okay, finally the temperature has stabilized near room temperature again, and the diodes are now back to their original wavelengths. And if you look carefully, you'll see the 3 individual stripes, which have become one singular stripe in the previous example when the temperature had been dropped to the different diodes. It's now substantially wider. There are 3 individual separate stripes that you can see, and it's about 3 times as wide. Instead of about a millimeter, it's about 3 millimeters wide. As sort of a conclusion here, I think probably the most important significant fact is the fact that this does work. And even with a temperature differential between 2 of the diodes as little as 6 to 7 degrees centigrade, I'm still able to get an overlap of the individual beams. And so I'm impressed that if this were done correctly, you might be able to stack as many as 6 or 7 diodes into a very tight, single beam from an array of separate but very closely spaced wavelengths. Another thing just to keep in mind is obviously this is a demonstration of these diodes in terms of the multiplexing. It in no way is supposed to represent the full manipulation of these beams. That's why I've allowed these large, tall stripes to exist, because there was no reason to try to draw them in. Clearly that can be repaired or that can be manipulated as a separate issue. But just like the anamorphic effect of these prisms, it wasn't the point of this demonstration, and so there was no reason for me to clutter up the table with spatial filters and beam correction apparatus just to get a nice round red beam at the end that would easily be achievable. Finally, the last thing I wanted to say is I've done everything I think I can do to demonstrate that this process is possible. What really is waiting now is a far better cooling system with a separate driver for separate channels that would allow many individually spaced and tightly controlled wavelength variations between these diodes to operate. I also think that I would go to a longer focal length aspheric lens, like a 4mm, to decrease some of the spread of the beam within the laser, just to make it a little bit easier to deal with. And also it's important with any of these high divergence diodes to march them back in their mounting so that ultimately the spacing between the first diode and the last diode in the series is exactly the same to any beam manipulation lenses that may be used later on. You cannot have one diode much closer to those lenses than another diode when they're all working within the same single beam. Otherwise, one will focus and one won't. And that's an important characteristic in any of my projectors, but something I didn't bother with the complexity of here because that wasn't the point of the experiment. One last little thing is this whole project has been an interlude in a much bigger project that I've been involved in, which is building an extremely high-powered pulse dye laser. I pushed that laser out of this room in order to make some space for this demonstration. But if you take a look over through this doorway here. So this is the project that's been put on hold for this other fascinating interlude. I'm going to go into this in a lot more detail later, but as you can see, this is a substantial investment both in time and money, and hopefully we'll do some really exciting things with this in the next several weeks. So I want to thank you very much for watching. I enjoyed doing this video like all the videos, and until next time.